Hello, this is part 2 of our series of lectures on inferential statistics. This is going to be about confidence intervals. In fact, we're going to focus mostly, or almost exclusively, on what's called a Z interval. So it's a confidence interval for the mean. So recall from our last lecture that we were talking about estimating a population parameter when all we had was information from a sample. And of course the best estimate of a population mean was a sample mean. It was a minimal variance unbiased estimator. That's an example of a point estimator. But the problem with the point estimator is that it's a single number and it varies from sample to sample. If we were to take a different sample, we'd get a different sample mean. All of them should be fairly close to the real mean, but none of them would be necessarily right on. And they don't give us a measure of how confident we are that that estimator is close and how close it might be to the actual target parameter. So our solution is to, instead of giving a single number, we give an interval. And we want that interval to be wide enough so that it is going to have a reasonable estimate, a reasonable chance of containing the target parameter that we're looking for that's unknown. So this interval is called a confidence interval. And for example, in this lecture, we're going to be mainly looking at a Z interval, and it's an interval of the form x bar minus some margin of error e up to x bar plus some margin of error e. So this margin of error is how far we go above and below our sample mean to create the endpoints of our interval. And so we notice that the right smack dab in the middle of the interval is our point estimator x bar. And what we hope is that the true mean is somewhere in this interval. Okay? And what we're going to do is we're going to use our knowledge of sampling distributions in particular, and also just general knowledge of the normal distribution, sampling distributions in general, probability and statistics, everything that we've learned in this course so far. We're going to put that to play here and put it to use to help us figure out this confidence interval, and we'll even know a level of confidence. For example, we might know that we're 95% sure, or maybe 90% sure, that our interval includes the true unknown value of mu that we're trying to estimate. So let's see what we can do about building this confidence interval. Now, before we even get started, there are a couple of underlying assumptions that we need to know to find this confidence interval for the mean, which is a Z interval. Okay, we're specifically focusing on this particular type of interval in this particular lecture. In later lectures, we will expand to look at confidence intervals for other statistics, or perhaps where the assumptions are slightly different. So the assumption number one is that the distribution of sample means is normal, or at least it's very closely approximated by a normal distribution. Well, is this a good assumption or not? Well, remember that the central limit theorem says that this is a good assumption if the sample size n is at least 30. No matter what the underlying distribution is, that the distribution of sample means can be approximated very well by a normal distribution. So we will use this for a large sample size, something at least 30, if we don't know anything about the underlying distribution. Now, if the distribution that we start with is normal, then of course any sample size will give us a distribution of x bars of sample means that is normal. And of course, if the distribution is not normal, but is close to normal for the distribution of individuals, then we can get by with a sample size that's maybe smaller than 30 and still get by with a good approximation of normal. So we need one of these two things to be true. We need to know that the underlying distribution of individuals is normal or very close to normal, and then we can get by with a smaller sample size and use the Z distribution. Or we can use any distribution as long as we know the sample size is greater than 30. So assumption number one is usually pretty good assumption. Assumption number two, however, is a little more suspect. it supposes that we know sigma sub x, the standard deviation of the population of individual measurements. This is usually not a good assumption. We usually do not know the population standard deviation. Okay? And we'll see later on what we can do to fix this. There's actually another type of distribution that's very similar to the normal, based on the normal distribution, but it takes into account if we don't know sigma sub x. So that's actually more often used, and that's called a t distribution, and so that'll be a t interval. We'll look at that a little bit later on, but for us to get the understanding of what's going on, it's actually better for us to start with this z interval, which is a little bit, assuming a little bit more than we usually really know, but it'll help us understand what's going on with the intervals a lot better than had we started with a t interval. Now later on in practice, the t interval is probably a more realistic and more often used example. So two assumptions. Number one, the distribution of sample mean is normal, and number two, that the standard deviation of the population is known. So here's our basic setup, and let's do this through an example. So we're going to look at this example, and this is a real world kind of example, but the data is actually made up, so it's hypothetical data. But we're going to use this example to help us understand what's going on with a z interval, and we're going to use this to help us derive a technique for finding confidence interval that we're looking for. So suppose we're interested in knowing the mean weight of all 7th grade boys in the United States. Now, think about it a minute. It's impossible to measure all of them. First of all, we could be talking about all 7th grade boys, past, present, and future, in which case there's no way we could measure all of those. Some in the past are dead, some in the future haven't been born yet. There's no way to measure them all. But even if we were just talking about all the 7th grade boys today, then even that is I guess theoretically not impossible, but it's completely impractical to measure all of them. So what do? We measure a sample. So let's suppose we take a sample that should be a random sample, should be a representative sample. And so if we take just a random sample of 36 boys and then find the mean weight of this sample. Let's suppose we do that and we find out that their mean weight is 100 pounds. And again, this is hypothetical data. I don't know what the mean weight of 7th grade boys is in the United States. This is just made up data. But let's go with it. Let's suppose this particular sample turns out to be 100 pounds for the mean. Now, we know that the best point estimator of the mean weight of all 7th grade boys in the United States is the sample mean. So at this point, our best estimate of the sample, of the mean weight, the average weight that is, of all 7th grade boys in the United States, our best guess is the mean of our sample, 100 pounds. Now, let's suppose something else. Suppose we know from history that the standard deviation in weights of all 7th grade boys in the United States is sigma, or sigma sub x, which is 12 pounds. Now again, that is a very unlikely assumption to have really be accurate in the real world. It's not likely that you're not going to know the mean of the population, but we do know its standard deviation. That's a little strange, and that usually doesn't happen. But for our purposes here, we're going to make that assumption to help us go forward with this. So we're assuming we know the standard deviation of the population is 12 pounds. That's the standard deviation of individual weights. Now, so suppose we do this again. We take another sample of another 36 boys and find their weights. We would expect the mean of the sample to vary a bit from the mean of the first sample. This time it's most likely not going to be 100 this time. It may be 101 or 102 or 98 or 99. It could be a little bit different from our original sample. And both of those could be different from the true mean of the entire population. Well, what happens if we do this over and over and over and over and over again? Each time we select 36 boys at random that are 7th grade boys. They're selected from the same overall population, find their weights, and compute a mean. Every time we keep the sample size the same, 36. Well, now these means will have a distribution all of their own. We sometimes call that a sampling distribution. So here's my question for you. What type of distribution does this set of sample means have? And then what is its mean and what is its standard deviation? Go ahead and answer these questions right now. Press pause. Well, let's take a look here. We notice that since the sample size is 36, which is bigger than 30, we don't really even have to know what the distribution of the rates of the individual boys is nationwide. We know that this distribution of sample means is at least approximately normal, perhaps exactly normal if the original population was normal, but at least approximately normal because we have a sample size larger than 30. This is a large sample. Okay, what's the mean of this sample? Well, whatever, we don't know what it is, but we know the mean of the sample is 100. What's the mean of the distribution of sample means? Well, that we don't know. It's the same as the mean of the population individuals. So we do know that the mu of all the x bars is the same as the mu of the x's. We studied this when we were talking about sampling distributions. What's its standard deviation? Well, if you remember, the standard deviation of the x bars was smaller than the standard deviation of the population. A sample has a tendency to be less variable than the population does. So sigma of x bar turns out to be the same as sigma of x divided by the square root of n. Now we know these things. We know that sigma of x is 12 when we know the n is 36. Square root of 36 is 6. 12 divided by 6 is 2. So we know that the standard deviation of the x bars is 2. Standard deviation of the individuals is 12. Standard deviation of the x bars is 2, but they have the same mean. So the sampling distribution, the distribution of x bars, has the same mean and a smaller standard deviation. Now let's suppose we know a little bit more information than we had originally. Suppose furthermore we know that the distribution of individual weights of all 7th grade boys, their individual weights are actually distributed normally. Well, then we know that the distribution of sample means is exactly normal no matter what the sample size is, and certainly with the sample of size 36, we're certainly got a normal distribution. Now suppose, unknown to the people doing the sample, of course, the actual mean of the population is mu, which is 101 pounds. Now if they really knew it was 101 pounds, this whole exercise would be a moot point because there's no point of estimating something you already know. But let's just suppose this is happening in the background. The true mean is 101 of the individuals, and yet our population mean, that is the population mean. The sample mean was less, it was 100. Okay, so we got a pretty good estimate, but not quite on. Now let's draw the graph of the probability density function, the PDFs, for the distribution of individual weights, and the sample means of weights of samples of size n equals 36, and draw them on the same axes. So get your calculator or computer to draw out these two distributions. Go ahead and do that now. Press pause. Well, these are both normal distributions, so we know how to draw these, say using a TI-84 calculator. To draw the bell curves, of course these are going to be bell curves, bell-shaped curves, because they are normal distributions. We enter the normal PDF, and so for example Y1 I put normal PDF of X, comma, then we put its mean and standard deviation 101 and 12. That's for the individuals. That's going to be the thinner line over here. I made the second line a little thicker by putting my cursor on this little symbol on the left of the Y2 and hitting enter until it looks kind of like a thick line. I think just once will do that. And then I did normal PDF of X, same mean 101, but this time the smaller standard deviation, which was just 2. And then I graphed both of these, and it turns out a window that makes sense. It should be centered up on 101, and I kind of centered it up on 100, and I went about 40 below and 40 above. And so we went from about 60 to 140, and since I did that I marked it off in 10 for the X scale. And the Y's, they don't go very high. Looks like, of course, the higher one's going to be the distribution of X bars, with the one with the smaller standard deviation. and it doesn't go up past 0.2, so I just used 0.2 for the highest y, and I did about a tenth of that and made it negative for the y min, negative 0.02, and maybe mark it off in 0.1s there, or maybe 0.01s would have been better, and graph that. And you can see the graph here, and you see two graphs, you see two bell curves. You see the lighter curve is the distribution of individuals, and the darker curve is the distribution of x bars. Here's the same graph generated in Minitab. So the red graph, the shorter, fatter one, is a normal distribution, 101/12. That is, it has a mean of 101 and a standard deviation of 12. That's the distribution of the individuals, the distribution of the x's. But the distribution of x bars, notice it's centered at the same place, centered at 101, but this time it has a smaller standard deviation, standard deviation of 2. So that's going to make it much more consistent, much less variable, smaller variance, smaller standard deviation, much more the area concentrated around the mean. So that makes it a lot taller and skinnier than the other one. Now the curve we're interested in really right now is the black curve, the distribution of sample means. So I'm going to do the next slide. I'm going to get rid of the red graph. I'm going to just keep the black graph only, but I'm going to maybe zoom in a little bit or change the window a little bit. And so this blue curve here is the same as the black curve on this particular picture here. Same as the darker curve on this picture. So the darker curve here on this picture, the black curve here, the blue curve here, the same ones, but I've changed the window a little bit. Looks like I've gone from somewhere around 90 something, 93 or 4, to about 108 or so. And the mean is right here in the middle, is 101, and this is a normal with mean 101 and standard deviation 2. And there's the graph of the PDF. Now, since this is a normal curve, we know all kinds of things about a normal curve. We know about some symmetry that it has, symmetry about the mean. We know about the bell shape to it. We know things about how to find probabilities with this using our shortcuts of our normal CDF. Of course, normal PDF is how we got this graph. And then we can also find x's with certain probabilities by doing an inverse normal. Lots of shortcuts built in for normal. So here's what we're trying to do now. We're trying to find an interval that we are reasonably sure that our interval will contain the true mean. By establishing a level of confidence, 1 minus alpha, we're going to establish a number that says this is the probability that the interval contains the true mean. And of course, alpha then is the probability that the interval does not contain the true mean, that it misses. So the alphas are sort of our probability we make an error here. Okay, so what kind of values do we usually choose for 1 minus alpha? Well, the usual suspects are 90%, 95%, 99%, but it could be anything. It doesn't have to be one of those values. It could be a 92% or an 83%. It could be anything. But those are the typical ones. And of course, the corresponding alphas are the complementary probabilities of 10%, 5%, and 1% respectively. So for this example, let's pick the 95% one. So we're going to compute a 95% confidence interval for mu. Okay. So let's take a look at our distribution and see what kind of an area would correspond to 95%. So the red area is an area of 1 minus alpha, or 0.95, 95%. That's a probability, remember. So what we've done is we've picked an interval that's centered up on mu actually. Okay, and we go to mu plus E and mu minus E, where E is our margin of error, and that's going to give us the limits there. So we've gone up and down about approximately 4 units from 101 to from about 97 to 105, and that's going to end up giving us a probability that's shaded there of 95%. Of course, half of it is above the mean, and half of it's below. So from the mu to the mu plus E, we're getting half of that. Which what would that be? That'd be 47.5%, and the other 47.5% is between mu minus E up to mu. Now that leaves alpha is the unshaded area, or the probability that it's not shaded here, and that is divided evenly because of the symmetry in the two tails. So each tail has alpha over 2. So if 1 minus alpha is 95% or 0.95, then alpha has to be 1 minus that, which is 0.05 or 5%. And then we want to split that into 2 pieces, so each one of those is alpha over 2, so that's 0.025 or 2.5% is in each tail. Okay? Now, what is this saying? It's saying that if we pick a particular x bar, this is the distribution of x bars. So if we pick a particular x bar, the probability that x bar is somewhere between mu minus E and mu plus E is 95%. That's the probability that it lands somewhere in that interval that corresponds to that red area. Well, if we knew ahead of time, and of course we don't, that mu was 101, then we could compute the values for the ends of the interval with our TI-84. Now, notice that 0.975 is the area below the upper end, and 0.25 is the area below the lower end. So let's look back at this a minute. We're going to use an inverse normal, and it's always an area to the left. So this area to the left of this one, if we want to find the 97.1, we don't know what it is yet. Okay, what we could do is we could say we do an inverse normal of this 0.025. We know that's the area to the left, and that'll end up giving us this 97.1. If we want to find this 105, we have to do an inverse normal of, well, all the area up to that from the left. So we need the 0.95 plus the 0.025. Or in other words, we need the 1 minus the 0.025. So we need to put in 1 minus alpha over 2. And so to get the right end one, that is 0.975 is the area to the left. And so we put that in, the mean, which is 101, and then the 2, so that's 104.919928, or about 105. And then we want to find the one on the left side. We do an inverse norm of 0.025, comma, mean of 101, standard deviation of 2, and we get 97.08007203, or about 97%. Not percent, a weight. These are actual weights. So we're saying that if we take the boy's weight between 97 and 105, that's going to account for 95% of all of the average weights of 36. Not necessarily 95%, actually not 95% of all weights of individuals, but rather 95% of the averages of samples of size 36. So now what is the E? The E is called the margin of error. Sometimes it's called the maximum error. And that's the distance from the mean to either end of the interval. So the width of the interval is twice E, 2E. So from the center mu to the top end, 105, that distance is E. And from the bottom, 97 to 101, that distance is also E. So E is about 4 here, roughly. So in this example, the margin of error is, well, you take if I round everything to the 10th, it's 104.9 on the top minus 97.1 on the bottom, divide by 2, and you get 3.9 pounds. So the margin of error is about 3.9 pounds. So, again, we're saying that there's a 95% probability that if we take a sample of size 36, that the x bar, the sample mean, will be somewhere in this interval from 97.1 up to 104.9. Alright, this is an important observation right here. So remember, 1 minus alpha is 95%. And that's the probability that x bar will be between mu minus e and mu plus e. That is, on the left end you got mu minus e, then you got x bar in the middle, and then mu plus e on the right. So x bar is between mu minus e and mu plus e. Well, let's solve this around. I'm going to subtract mu from all three sides. So that cancels out the mu's on the outer sides, and in the middle leaves us with x minus mu. So we know that the opposite of e is less than or equal to x bar minus mu, which is in turn less than or equal to e. Now I'm going to subtract x bar from all three sides, and so we get minus x bar minus e is less than or equal to minus mu, which is less than or equal to negative x bar plus e. Now I'm going to multiply all three sides by negative 1. That's going to give us x bar plus e, then mu, and then x bar minus e. But remember, when you multiply an inequality by negative 1, it reverses the direction. So now we have x bar plus e is now greater than or equal to mu, which is in turn greater than or equal to mu to x bar minus e. If we rewrite that in the normal order from left to right, is increasing to decrease, the smallest to largest in an increasing order, then that's going to be x bar minus e, which is less than or equal to mu, which is less than or equal to x bar plus e. And so we're saying that mu is an element of this interval from x bar minus e to x bar plus e. Notice what we have done here. We've reversed this around. We've said we started with the distribution back here, which is a distribution of x bars. This distribution here, or here's another picture here. And we know that this area is 1 minus alpha. That's the probability that x bar is in that interval between mu minus e to mu plus e is 95%. So what we're doing is we're assuming this distribution is out there somewhere. It's known. Well, it's maybe not known, but it's out there. Okay? And we know that the probability that x bar is in that interval from mu minus e to mu plus e is 95%. But we just saw that if x bar is in that interval, then mu has to be in the interval x bar minus e to x bar plus e. So we turned it around. We've turned it around where the first interval, where we sort of knew mu, and we went left and right from mu, and used our information that we know about sampling distributions and normal distributions to say, well, what's the 95%, what's the right e to choose so that we get 95% probability that x bar is in that interval. Well, it turns out that it's exactly the same probability if we sort of rework it like we did on this page and get mu to be now an interval, is in the interval from x bar minus e to x bar plus e. So it happens that x bar is an element of this interval mu minus e to mu plus e exactly when mu is an element of this interval x bar minus e to x bar plus e. The interval at the bottom, x bar minus e to x bar plus e, that's our confidence interval. So just as we're 95% sure that x bar is in this interval from mu minus e to mu plus e, we're equally 95% sure that mu is in the interval, our confidence interval, from x bar minus e to x bar plus e. Alright, that's very important that we were able to reverse that around. Okay? And so, whoops. So there's a 95% probability that x bar is in the interval from mu minus e to mu plus e. But this is equivalent to a 1 minus alpha, or 95% probability that mu is in the interval x bar minus e to x bar plus e. This is our 95% confidence interval for mu. So notice it's based on understanding that we have a distribution of the x bars that's normal. Okay, so that was a very, very important assumption for this. Now, in reality, though, we don't know mu, right? So we don't know what this distribution is back here, this distribution here. But it turns out if we could just figure out how many standard deviations we were above and below the mean here, we could compute z-scores for these, and we get a distribution here for the normal distribution that's a standard normal. So the standard normal distribution, and we get the same area, so we can get 0.95. Well, we know all about a standard normal, and we can figure this out. So what we've got is this guy here in the middle is 0 for the mean. Of course, that's mu minus mu over sigma, which is 0. And that's 0. And then over here we have, on the top and below, we have what we call z alpha over 2, which is the one on the right. Now, this is kind of different notation here. When it says z alpha over 2, it means the area to the right of this number, in this case the 1.96. The area to the right of that is alpha over 2. Okay? Not the area to the left, which is what's generally done with a CDF. Okay? So, that's going to be our whatever our margin of error is. Okay? That should say, yeah, if we subtract off our mu and then divide by sigma. So this is mu plus e, subtract mu, now you're back to e, then divide by the standard deviation of the x bars. So this is e over the standard deviation of the x bars is z alpha over 2. And of course this other one, because of the symmetry, is just minus z alpha over 2, and that's just the opposite of e over sigma of x bars. So this right here, this is an important formula, that z alpha over 2 is e over the sigma of the x bars. So here it is again. Here's how we did that again. It's mu plus e minus mu, which is just e over sigma of x bars, and that's z alpha over 2. So again, z alpha over 2 means it's the z value, that's the x value on the standard normal distribution, okay, which we're going to call the z distribution, or the z value. And it's an area, but it's the particular z value, so that the probability that x is bigger than that z value is alpha over 2. So this unshaded area tail on the right has area alpha over 2. Well, we know how to do that. That means that the area to the left is 1 minus alpha over 2, and that's what we need in our calculator. So for a TID4, for example, we want the area to the left to be the input for the inverse normal. So we use the inverse norm command, but we put in 1 minus alpha over 2. So notice that they're typically either going to give you alpha, or actually normally they're going to give you 1 minus alpha first. So you're going to start with 1 minus alpha. From that you figure out alpha, then you figure out alpha over 2, then you figure out 1 minus alpha over 2, and that's what goes inside the inverse norm to get z alpha over 2. So now remember, we're assuming we know sigma, so this gives us a nice relationship between the margin of error, the sample size, and the confidence level. So in other words, we want to give us a relationship between e, n, and, well, 1 minus alpha or just alpha. Okay? And, of course, sigma of x bar is sigma of x's divided by the square root of n. When I say we know sigma, what I mean is we know sigma sub x, the standard deviation of individuals. And what we're dividing by here in the formula for z alpha over 2 e over sigma of x bars, that denominator is sigma of the x bars. Sigma of the x bars, again, is sigma of the x's divided by square root of n. But that's also, instead of writing as z alpha over 2, let's go ahead and go to the calculator version, which is inverse norm of 1 minus alpha over 2. So we have this formula at the bottom of the page here that's important. It says our margin of error e is the sigma of the x's over the square root of n times the inverse normal of 1 minus alpha over 2. Again, that we assume that we established some level of confidence to begin with, so we know what 1 minus alpha is. From that we figure out alpha, then we figure out alpha over 2, then we figure out 1 minus alpha over 2. So we're going to know the input for that inverse normal part. We're assuming that we know the standard deviation of the population individuals. We know sigma sub x. It's given in the problem. And then finally, we're going to know the sample size, so we can plug that in. We can plug those three numbers in, sigma sub x, alpha, and n, into this formula and come out and find the margin of error. Once we find the margin of error, we know the confidence interval because it's just x bar minus e up to x bar plus e. So let's look at an example. Let's look at the same example that we have. So the first step is to record the known standard deviation, which was of the x's. Sigma sub x is 12. Next, we collect data and measure the sample mean and the sample size. N was 36 was the sample size. The sample mean we measured to be 100. Then we establish the level of confidence that we want. So in this case, we wanted 1 minus alpha to be 95%. We're finding a 95% confidence interval. So that means alpha is, so it means 1 minus alpha is 0.95. Do 1 minus that, you get alpha, that's 0.05. Divide that by 2, you get 0.025. And 1 minus alpha over 2, 1 minus 0.025 is 0.975. And so that's really the 0.975 is what we're going to need. Now we compute the margin of error by just plugging in the formula. Sigma sub x is 12. Divide that by the square root of n, that's the square root of 36. Of course, we already worked that out earlier, that's 2. And we multiply that by the inverse normal of the 1 minus alpha over 2, that's the 0.975. And that works out to be 3.91997,972. Same number that we were looking at earlier. Okay, now, what is that margin of error? Okay, that's how far the interval goes from the mean above to the top of our interval, and from the mean down to the bottom of our interval. So our interval, our confidence interval we're looking for is x bar minus e to x bar plus e. Remember, x bar was 100. Our mean weight was 100 of our boys that we measured in our sample of size 36. So that's 100 minus the 3.91997,972 up to 100 plus the 3.91997,972, or approximately 96, that should say 0.08 up to 103.92. And you can see some of the computations on the calculator screen on the left. So that is how we build a confidence interval. So now that we've built the confidence interval, let's make sure that we understand what it means. So the blue interval is our confidence interval. It goes from 96.08 to 103.92. Right smack dab in the middle of that is 100, which is our sample mean. And you can see that illustrated by the blue interval, and you also see 100 right in the middle of the interval there. Notice that the mean of 101 is a little above the 100, our sample mean, but it is definitely within the blue. So just as the 100 is within the red, our sample mean is within the red, that will happen exactly when the actual mean, 101, is within the blue, which it is. So the probability that x bar is between mu minus e and mu plus e is 95%. The probability that x bar is in the red is 95%. In this case, it actually is in there. And the probability that mu is in this interval from x bar minus e to x bar plus e is also the same probability. Also notice that the width of this blue interval, how long it is exactly how long the interval is there on the x-axis that corresponds to that red region. Now, it's very important that you understand this. It's not the mean that is moving. So when we do a confidence interval, it says we can say it this way. We can say, well, if it's a 95% confidence interval, we can say there's a 95% chance that the mean is actually in the interval. But don't confuse yourself. The mean is something that's out there that's fixed. It's not that the mean is moving around. If we do this over and over again, the mean's going to pop around, and 95% of the time it's going to be in an interval. No, it's exactly backwards from that. it's the intervals that are changing from time to time. The distribution, whatever it is, of course it's actually unknown, but in this case we're assuming that really in the background this distribution is what you see pictured in the picture there, and the red area is the probability of the confidence level, 1 minus alpha, 95%, and it's centered on the true mean of 101. Then we have the intervals here, the blue intervals. And what if we repeat this? Now we're going to repeat this in such a way that we get the same margin of error E and the same sample size N, and so that's going to make the interval widths always the same. Okay, so the length of these little intervals that we have here, mostly blue, there's one red one, that all these intervals have the same length, and they're centered up on whatever the sample mean happens to be. Well, if we're 95% sure that this is going to happen, that these are 95% confidence intervals, what that means is if we repeat this process over and over and over and over again for a very large sample of these sample confidence intervals that we come up with, that on average about 95% of them will actually contain the true mean. And of course, exactly when that happens, that means that the center of these, the x bar, will be in the red up in the true distribution up above. So, of course, 95% is 19/20ths, so that says roughly 19 out of every 20 will contain the mean. And I've, of course, made up some data here, but in my made-up data, I have 20 intervals, and exactly one of them, the red one, does not contain the true mean, but the other 19 do. And so that illustrates that, on average, about 1 out of every 20 intervals that you do this way will not contain the real true mean. But 19/20ths of the time, that is 95% of the time, they will contain the mean. So you can see the true mean coming down there at 101, and you can see it going through the blue intervals, but it misses the red interval. So 19 out of 20 times this works out. So notice again, let me emphasize this again. It is not correct to say that that the confidence interval means that the mean is moving around and that 95% of the time it's actually in the interval. That is not correct. What is correct is the intervals are moving around from one sample to another sample, and 95% of the time those will contain the actual mean. It is correct to say that there's a 95% chance that that interval will contain the mean, but make sure you understand that it's the intervals moving, not the mean. Now, if you notice this formula that we have here, E equals sigma of x over square root of n times inverse normal of 1 minus alpha over 2, contains alpha, n, and e. Okay? And so we have sort of a three-way tug-of-war going on here among these three different things. What do we want? We want to have a very high level of confidence that our interval contains the true mean. I mean, an interval that only has a 10% chance of containing the mean is not very useful, because there's a very high, it's more likely the mean's not in the interval than it is. We want an interval, we want a high level of confidence, and I've already told you that the typical suspects there are a 90% confidence interval, 95%, or even 99%. So we want that to be very, very high level. Now, of course, we can make it 100%. How do you do that? Well, you just make it go from minus infinity to infinity. We know that's going to contain the mean. But that's not very good either, is it? Because that doesn't narrow it down at all. Well, on the other hand, what would you like that? You'd like that interval to be small. You'd like it to not be a very big interval so that you can really narrow down where the mean really is. So you want that margin of error to be small. Okay? Well, let's say we fix a sample size. Okay? Then that's fixed. Then we've got the high level of confidence, a low margin of error. These things are working against each other. the higher we make the level of confidence, the lower we're going to make, the higher we're going to make that margin of error. Okay, like I said, we can make it perfectly 100% on confidence, but to do that, we've got to make the margin of error infinity. On the other hand, we can make it a very, very low margin of error. We can say, okay, well, make it within, half a pound either way. For example, in our weight example, the problem with that is we may only be we may only be 20% confident that we could get something in that range. Okay, that was made up number. But the point is that high confidence is going to make your margin of error go up. If your margin of error goes down, that's going to make your confidence level go down. Now let's throw in the sample size n. Well, the sample size n has a tendency to, what we want is a low sample size. Why? Well, because it costs money to measure stuff. So what we really want is the lowest sample size that will actually achieve the results that we want. So let's say we fix a margin of error that we want, then the lower the sample size, the less confident we're going to be. Or if we fix our confidence level, okay, we fix the alpha basically, and we look at the formula here. For E, the bigger n is, the smaller E gets. The smaller n gets, the bigger E gets. If you just look at the formula, you can see that, right? Because you're dividing by the square root of n. The bigger n is, the bigger the square root of n. And the bigger the thing you're dividing by, the smaller the thing is on the right side. And so, in fact, these things are working against each other. So all three of these things are kind of working against each other, and they're tugging in different directions. So what you have to do, of course, is make some kind of balance among these three things. You make a sample size that's reasonably big enough to where you can actually go out and measure it without being too costly, but at the same time it leaves you with a level of confidence and a level of margin of error that you can live with. And so you work these three things around. Now in the example we've done so far, we assumed the sample size right off the bat. We fixed that at 36, and we fixed our confidence level right off the bat at 95%. And the thing that we went to find out was the margin of error. And this formula that we have at the bottom relates these three things, and it's the way it's solved for E. So if you know alpha, you can plug that in here. If you know 1 minus alpha, you can find alpha, then find alpha over 2, then find 1 minus alpha over 2. And then you figured out what goes inside this parentheses for the inverse normal. And again, I'm using the TI-84 notation there for inverse normal. We're assuming we know sigma sub x, and what we do is we just put in the sample size n in there, so you're taking the square root of n in the denominator, dividing that into sigma of x, multiplying by the inverse norm of 1 minus alpha over 2, and out pops E. Then your interval goes from x bar minus E to x bar plus E. So this version of the formula solves for E if you know alpha, sigma of x, and n. Now, we can take the same formula, and another way of saying that was E is z sub alpha over 2 times sigma sub x over square root of n. Now, the z of z sub alpha over 2 was exactly this inverse norm of 1 minus alpha over 2. Okay, so I just used the typical abbreviation of z sub alpha over 2 for that. Now, what we want to do is solve this for the sample size. We're going to take the same formula, just solve it for the sample size. So let's see, we're going to start by multiplying both sides by square root of n, and then divide by e, and then finally square both sides. And so we get n is z alpha over 2 times sigma of x divided by e, and then square that. Or now let's put the calculator notation back in. Instead of z alpha over 2, I'll use inverse norm of 1 minus alpha over 2, which is the way you've got to actually do it in your calculator. So, n is the inverse normal of 1 minus alpha over 2 times sigma of x divided by e and square it. So if you know ahead of time here basically what confidence level you're going to know, you can use 1 minus alpha to figure out what 1 minus alpha over 2 is. Figure that inverse norm with your calculator. We know sigma sub x, put that in. We know the margin of error this time that we're willing to live with. And then we can use this formula here then to figure out what sample size we've got to use. And of course, any bigger n than that would work out. Of course, n has to be usually a sample size, so it has to be an actual whole number usually. And so for that to work out, then, well, I say usually, almost always basically, n is a whole number, so n you round up. Okay, always round up to the next one, even if if n turns out to be 7.3, you're going to go ahead and say, well, it's got to be bigger than that, so it's going to be 8. Something bigger would work fine. It would make it even nicer. It would even make a smaller margin of error or more confident, depending on which one you wanted to do. But so you could go with a larger sample size if you want. But this will give you the sort of the minimal sample size you can get by with. So here's the same basic formula solved 3 different ways. The first one is basically where we started. We said, okay, what is 1 minus alpha? Well, 1 minus alpha is the normal CDF from x bar minus e to x bar plus e with the standard, with the mu of, or the centered at x bar, and then that's the mean. And the standard deviation was the standard deviation of the x's divided by square root of n. And so that's using the TI-84 notation there. And that gives you 1 minus alpha, the confidence level. Okay? And that's sort of kind of the way we started building this thing. Now, if you're going to actually build the confidence interval, then you need to find out what E is. And to do that, we sort of solve that same equation around for E, and that gives us E is sigma of x's divided by square root of n times the inverse normal of 1 minus alpha over 2. And as we just saw on the previous slide, we can take that same formula, solve it for n, and that's inverse normal of 1 minus alpha over 2 times sigma of x over E squared. Now, let's use this last version in an example. Now, to a new example here, suppose we're measuring the average salary of residents of Fort Smith, Arkansas, and we want to produce a 90% confidence interval for the mean salary, and we want our margin of error to be no more than $2,000 per year. Furthermore, suppose that we know that the standard deviation of all salaries is 16,000 per year in our population, and what is the minimum, so our question is, what is the minimum sample size needed for a study to produce this confidence interval? Now, of course, the only part of this that's unrealistic is knowing the standard deviation of all salaries. But again, that's our sort of simplification that we've been assuming for this entire lecture. We will relax that assumption a little bit later on and show you how we have to adjust these techniques just slightly to work this out if that's unknown, which again is more likely. Now, notice that this is a reasonable way to proceed. We know we want our interval to be 90. We want to be 90% confident that our interval that we produce is going to contain the mean, and we don't want it to be too big. We want to be able to zero in on that mean within $2,000 above or below. So we want to. So this is going to give us a interval that's going to go from x bar minus 2,000 to x bar plus 2,000, or in other words, an interval that's going to be $4,000 wide, and we hope that our true mean is going to be in there, and we're going to be 90% sure that that's going to actually happen if we choose the right sample size. So what sample size do we choose? Okay, so let's look back at this. If you look back at your data, you can see from what's written in the paragraphs, we know that sigma of x's is $16,000 per year. We want our error to be less than or equal to $2,000 per year. And we want 1 minus alpha to be 0.90, that is 90%. Now if 1 minus alpha is 0.9, then alpha has to be 0.1. Alpha over 2 is 0.05, and 1 minus alpha over 2 is 0.95. Okay, use this to now figure out what n is going to be based on the formula we had from before. Okay, let me give you a little hint. Let me back up. Here's our formula. We want to use this bottom formula right here. Jot that down real fast. Okay, got it? Okay, now let's go from here. Go ahead and figure out what n is. Press pause now. Okay, here we go. So n is inverse norm of 1 minus alpha over 2 times sigma of x over e, and then square the whole thing. So put in our numbers. Sigma of x's is 16,000, e is 2,000, and of course that's, divide those out, is just 8. But I've typed it all in the calculator. And of course 1 minus alpha over 2 we figured out is 0.95. So you can see here in the calculator that is parentheses inverse norm of 0.95 times 16,000 divided by 2,000, close parentheses, square the whole thing, and you get 173.1547808. But n needs to be a whole number, so we round up to the next one up, which is 174. And so if we use a sample size of 174 or bigger, we will get at least a 90% confidence interval that is going to have a margin of error 2,000 or less. So when we're going out and doing our samples, we better make sure our sample size is 174 or more. We don't want to make it too much bigger than that because it's going to be costly to go out and survey and find out these salaries of a random sample. Okay, but on the other hand, we can't get by with less than 174 if we want this level of accuracy on our interval.